Okay, so Mrs. Jones, now I'm also recording on swivel. I'm recording both the lecture and I'm recording the screencast at the same time. So, and you can tell me later how this looks on your screen, and is it jumpy and is it actually work? So anyway, last time we started talking about the ultraviolet series, and we talked about the amounts of energy that were going to be released or were required to have electrons jump from one energy level to another. And we said if electrons went down to the first energy level, we're going to get ultraviolet light because that's a greater amount of energy drop. If they went to the second energy level, they're going to give off visible light, and then if they go to the third energy level, they'll give off ultraviolet light. And the thing that you need to have an ability to do or an ability to understand, and I'm going to go ahead and stop the meeting now here so I'm going to go ahead and stop the meeting, Kelly. Was that adequate? Did that work? Good. Thank you. So let me. So the meeting. How do I stop the meeting? And meeting for all. Okay. So that was just a test to see if we could live stream and record at the same time. Okay, so anyway, the thing that we want to do is we want to connect this information to the spectra that we see, and we have a little spectrum here, and it's in nanometers. And remember that the ultraviolet light is generally going to be below 450. And then visible is going to be up to about 750, and then infrared is going to be longer wavelengths than that. And remember, the longer wavelengths mean less energy, a little more energy, a little more energy. And then we said that the fact that these lines got closer together, as we go to more energetic wavelengths, meant that the amount of energy between these energy levels got less and less and less. And we said that was because these electrons were getting further and further away from the positive charge of the nucleus, so it took less energy to jump up to each next energy level. Okay, so that's the understanding of this that we need to have. And you don't have to know numbers like this or anything, but you have to be able to interpret what numbers like this meant. So if you were given this list of numbers here, you would need to be able to see, well, there's about a 0.3 difference between that and about a 0.11 difference between. You would need to be able to say that you could see that these amounts of energy were decreasing the more that I got farther away from the nucleus. Okay, and also recognize that at some point we completely escape the nucleus. This electron leaves the nucleus, and I told you before that when we talk about ionization and electrons leaving the nucleus, like a metal atom, a sodium atom, we lose that electron. We pretend that it's very easy for those atoms to lose an electron. But, is it really that easy? We have to supply some energy to cause that electron to lose, or that atom to lose the electron. So in the process of ionization, when I have a sodium and a chloride coming towards each other, this doesn't just automatically happen that the electron leaves the sodium atom and goes to the chlorine atom. and then I get a +1 and a -1 charge, right? This doesn't just automatically happen. There has to actually be some energy in the system supplied that creates that electron leaving the sodium atom. It's not as easy as it sounds. So some energy has to come from somewhere. But once the reaction starts, all kinds of energy is going to be released, and it's going to cause all kinds of these sodium electrons to lose their electrons to be ionized. Anyway, we walked through these questions here, and so we said, as the wavelength for each line becomes shorter, what happens to the frequency of the wavelength? And so as the wavelength becomes shorter, the frequency gets greater, right? So the shorter the wavelength, let's see, the shorter the wavelength, the greater the frequency. The energy, let's see, what happens to the energy released contained in the photon? That also increases. Because the energy is lost by the system when an electron moves to a lower state, we represent these as negative values. Okay, so this state here, this ground state, when I'm at the lowest energy level, I'm at -2.178 times 10 to the -18th joules, less than what I would be if I was not part of the atom. Okay, so the fact that this electron attaches itself to an atom, if it just came out of nowhere, the energy state of that electron and that proton would be such that if they're not together in the same atom, they have this much energy is more than if the electron's at the ground level. So if the electron's at the ground level and it just came out of nowhere and attached itself to this proton, we would lose this much energy. So we've got this much energy less than what we had when we were just a proton. And this will become clearer. We talked about, what do you notice about the energy required to push an electron further and further away from level 1? It got less and less, and we said that because it was farther away from the electron. And then how is this reflected in the distance between the lines in the spectrum? They got closer together. And that's kind of where we stopped, wasn't it? Okay. So the last value in the list says from infinity to level 1, this represents the point at which an electron is removed from the atom and is no longer under the influence of its nucleus. And so this is the amount of energy it would take to remove an electron from the hydrogen atom at the beginning point of level 1. Because removal of a hydrogen or an electron from an atom results in the formation of a hydrogen ion, the energy that causes this is also called the ionization energy. And so this is a property of every atom. Every atom has outer shell electrons, right? And to remove one of those electrons, I have to supply energy. And this is called the ionization energy. So the ionization energy is a property of every atom. Okay? If I do the same thing for the visible series, and again, that's going to be this series right here. Here's the line, and you don't need to know these names, but to go to the first energy level, to go to the second energy level, is this series here. And anything beyond this is just going to release infrared radiation. But for going to the second level, we release visible radiation. What do you notice about the wavelengths of light emitted in this series compared to the Lyman series? What do I notice about the wavelengths? Are they longer or shorter than in the ultraviolet?
Shorter. No. Longer?
They're longer, aren't they? Okay, and that reflects the fact that they have less energy, right? And so you can ask the same question about the frequencies. The frequencies are going to be less. If I've got longer wavelengths, I've got longer or lesser frequencies, and I have lesser amounts of energy associated with those transitions. Okay, so compared to the Lyman series or compared to the ultraviolet series, the wavelengths are longer, the frequencies are less, and the energies are also less. Again, notice that the longest wavelength in the series represents the smallest transition. Again, notice that the transitions are to higher and higher levels. As you go to higher and higher levels, the energy becomes smaller and the distance between the lines becomes shorter. And I don't know why it's taking so, it's probably memory problems. Okay, so in the visible series, again, they're getting shorter and shorter between. And then, sorry about that. Okay, and then, oh, that's still the visible, or the ultraviolet. And there's the visible. And then with the infrared series, each of the line represents the frequency of light emitted when the electron moves from an outer to the third energy level. And it's the same kind of thing here. We have even longer wavelengths, we have lesser frequencies, and we have lesser amounts of energies. And why are you slowing down so much? Okay. Now, also a final point, we'll notice that the lines of the shortest wavelengths will also have the greatest intensities. The lines with the shortest wavelengths are going to have, that the lines of the shortest transitions will have lines with the greatest intensities. And what I mean by that is, if I go from here to here, well, actually, let's just use visible light because that's what we see. If I go from the second energy level to the third energy level, I'm going to have a greater intensity of light than if I go from the second energy level to the fourth energy level, or if I go from the second energy level to the fifth energy level, or the second energy level to the sixth energy level. Why am I going to have a greater intensity of light if I just go from here to here and then back? Yeah.
Is it because of the shorter distance?
Okay, that's part of it, but what is that? What's the consequence of it being a shorter distance? It happens. If I only have to add a little bit of energy to go from the second to the third level, whereas I have to add a lot more energy to go to this level, how often is each going to happen compared to the other? Am I going to go to the shorter distance more often, or am I going to go to the longer distance more often?
The shorter distance.
I'm going to go to the shorter distance. It's easier to do, right? It's easy enough to do. I'm going to do this all day, and I'm going to do this less often, and I'm going to do this less often. So I'm going to have a greater light intensity. And it's not showing it really well here, but in the visible light here, this light is a little more intense than this one, just a little bit, and that's more intense than this one, and that's, but as I go to longer jumps, I don't do it as frequently, so I have fewer transitions, and I have less intensity of that light. So the intensity of the light is going to reflect how often I make that jump. And I'm going to jump here a lot more often than I'm going to jump all the way out here. Okay, so the spectrum really does give us a lot of additional information other than, oh, it's just this wavelength of light that's being emitted. Okay, we can get a lot of information from this. This tells us about the energy differences between the energy levels. Okay, it tells us about the energy differences between the energy levels. And because I know how much energy is related to each of these wavelengths of light, I can tell how much energy difference there is between each energy level. Now you may have wondered, well, you talk about these energy levels like you can actually measure that amount of energy, that tiny amount of energy difference, between here and here, it's 0.3 times 10 to the 18th joules of energy to go from here to here. How can you possibly measure that? Well, this is how we measure that. We see what the light emitted is, and we know what the energy of that wavelength of light is, and we make the correlation. Okay? And so that's pretty impressive. The spectrum of these things is full of information that you wouldn't think about to begin with. So, all of this led to something called the Bohr atom of the model, or the Bohr model of the atom. A model of the atom based on the idea that only certain changes in potential energy states are allowable, and I make those changes by absorbing or emitting quanta of energy. And again, remember that this is something that we did not anticipate. We only thought that adding or removing energy from something either sped it up or slowed it down. We didn't realize until we started seeing this and understanding its significance that this represented a change within the atom itself, not the whole atom, right? We're not speeding the whole atom up or slowing it down. We're making potential energy changes within the atom. And you have to remember that although that seems like a tiny amount of energy change, and that doesn't affect anything, does it? That amount of energy change. If we have even just 1 mole of these atoms that are all doing it at the same time, that's 10 to the 23rd atoms that are doing, that's sextillions of atoms that are doing this at the same time. And so that all adds up to lots and lots of energy. Remember, we're seeing 1 times 10 to the negative 18th joules of energy being changed every time an electron moves, but I'm talking about 10 to the 23rd atoms. If 10 to the 23rd atoms have their electrons changing energy, that's thousands of joules of energy that are changing. So it's easy to get the idea that this is sort of meaningless and insignificant, but it's everything. Okay, so Niels Bohr unfortunately couldn't let go of the idea that the particles had to follow some kind of path. This is 1913, and de Broglie didn't come up with his hypothesis that particles can travel as waves until the 1920s. So we still hadn't quite figured out that electrons predominantly have a wave motion as opposed to a linear kind of motion. Okay, so he couldn't let go of the idea that these things probably traveled in some kind of an orbit. Okay, so although he was aware that according to everything classical physics knew, an electron in a circular orbit should lose energy and be drawn into the nucleus, he ignored this and still proposed that electrons were in a circular orbit around the nucleus. His thought was that electrons simply just don't do this. Okay, they don't collapse into the nucleus. And that was all he would say. Electrons just don't do that. But because energy could only be gained or lost by the atom in certain quantized amounts, and these quantized amounts could be determined using line spectrum data, using the laws of classical physics, Bohr determined a theoretical radius of each allowed orbit based on how far each amount of quantized energy would push the electron away from the nucleus. Okay, now again, there aren't any orbits. He thought there were, but there aren't. But he determined a theoretical radius of each orbit based on how far the amount of quantized energy would push an electron away from the orbit, based on classical physics. Okay, so he said that the radius of this orbit should be this, based on how much energy is being added to the electron, the mass of the nucleus, or the mass of the electron, the mass of the proton, that kind of thing, and the electrical charge. How far would that amount of energy push an electron away from the nucleus? So according to the model, when the correct amount of energy was absorbed, the electron jumped from one orbit to one further out, or when the correct amount of energy was lost, the electron moved to an orbit closer in. Again, although he thought there were only certain allowable orbits and amounts of energy, he didn't know that the amounts of energy, what the amounts of energy were based on. He didn't know why the electrons should not be drawn into the nucleus. Okay? And it's because they're not traveling in an orbit, right? They are going to get sucked into the nucleus. Their whole waveform covers the space around the nucleus. They can't get sucked into the nucleus because the space that their wave vibrates in is surrounding the nucleus and containing the nucleus. Bohr's model allowed him to create an equation to determine the amount of energy present at each energy level of the hydrogen atom. It was known that the amount of energy required to completely remove an electron was 2.178 times 10 to the negative 18th joules of energy. That is, the hydrogen atom had to absorb this amount of energy to become ionized. We also say this represents a state where the electron is infinitely far away. And so the quantum number of the atom is n equals infinite. Okay? It doesn't really matter where it is. It's just not in that atom anymore. And remember the energy change related to the ultraviolet photon released when an electron transitions from the infinity state to the ground state is that same amount, right? It takes that much energy to kick it out, but if I bring it in from outside the atom, I lose that much energy. Therefore, when an electron of a hydrogen atom is in the ground state, or energy level 1, we say that it has a quantum number of 1. And this is where the term quantum comes from, the energy level. It's the number of the energy level. Okay, so it has this much joules less of energy than when it's ionized. So if we let the ionized state represent an arbitrary reference level of 0, okay, we're going to say that the ionized state of the electron is a state of 0. We don't know how much energy it actually represents, do we? Okay, so if I've got these energy levels, 1, 2, 3, 4, 5, 6, 7, and I've got my electron out here, okay, we're going to say that at this point, the energy of that electron is 0 joules. It's just an arbitrary reference, okay? That's why all these numbers are negative, okay? If I get into this energy level, I have a little bit less than 0. I've got an absolute value of number less than this energy here. I lose a little bit more energy, and I've got a little bit more less than 0. Finally, I get down here, and I have negative 2.178 times 10 to the negative 18th joules. I have this much energy less than I had when I was out here. That's why these numbers are negative. Okay? Therefore, the energy levels of a hydrogen atom range from 0, when the electron is completely removed, to negative 2.178 times 10 to the negative 18th. Okay? Now, what would have been more acceptable of a way to do this to our minds? Not set 0 as this level out here and that this is a negative amount of energy, but what would have been more acceptable to us? probably. Maybe set this to 0 and increase the numbers positively as you go away. Okay, so they didn't do that though. They set this number out here as 0 and these as negative, even though that doesn't necessarily make sense. And there are reasons for it that you would probably learn about if you took higher level physics in college. Okay, now we've already seen how much energy is emitted for various transitions of electrons. Using his knowledge of these spectra and his predictions based on classical physics, Bohr created a formula that predicted the energy level within that range. Okay? And this is the product of the energy of the ground state times the ratio of the square of the nuclear charge. The nuclear charge is Z. And it's going to be 1 for hydrogen, right? Because I've got 1 plus or 1 proton. So that's going to be 1 squared. And this is going to be the quantum number. And that's going to be squared as well. So first, notice this correctly predicts the energy of the ground state. If I have a proton and I have my first energy level, this correctly predicts the energy of the ground state. Okay? If I have 1 squared over infinity squared, this correctly predicts that the amount of energy that I have is 0. So if we predict the amount of energy of the second energy level, 1 squared over 2 squared, so 1/4 of this value, that gives us negative 5.445. And we go and look at the data from above. From the line spectra data above, we know that when an electron transitions from the first energy level to the second energy level, it absorbs this number of joules of energy. If I subtract that, or I'm sorry, if we add this amount to the ground state energy, we get this number. And that's really close. So the Bohr formula predicts the energy levels of each of these states. Now, you're not going to need to know that formula. You just need to know that Bohr was able to create a formula that predicted the energy of each of these energy levels. Okay? Although we could, if we wanted to, calculate the energy released when a hydrogen electron transitions from a level 5 to a level 2. Again, you're not going to need to use this. This is just an example of how that could be changed. Also calculate the wavelength of light that is emitted during that transition. Remember that the change in energy is the final state, the initial minus the initial state. Compare this to the value listed in the visible series above for this transition. If we did this, we would find out that what we predicted based on the Bohr atom would give us a value of the wavelength of light that's very close to what we would predict. Again, we're not going to need to do that. And I'm just showing you this just because it's possible. And you need to have the understanding that there's a way to do this. So an easier way to find the change in energy for an electron is to modify the original Bohr equation. And what we could do is we could say the 1 over the final quantum number squared minus 1 over the initial quantum number squared, and multiply that times the energy of the ground state. We're not going to do that again. We're just going to talk about the significance of this. Although his model accurately accounted for the energy differences between each theoretical level, when the same reasoning was applied to other atoms, it didn't work. Okay? And there's going to be a couple of reasons for that. Although his model showed that a quantum approach to the structure of the atom was necessary, okay, we need to structure our model based on the idea that we have energy levels, and that's what this showed. Bohr's model was flawed at its core because it didn't include an explanation for why energy changes are quantized. So what ended up happening is that when I got a second electron in the mix, or a third electron in the mix, or a fourth electron in the mix for higher number of electron atoms, it made it so that this formula didn't take into account for the effects of those electrons. Okay, and what kind of an effect would one electron have on another as far as, you know, influencing its energy? What's one electron going to do to another electron, since they're both negatively charged?
Would they? Oh, they're both. No.
They're both negative. They're going to do what?
I want to say repel.
They're going to repel each other. Okay? So, although I've got a nucleus that's attracting all of these electrons, okay, if I have multiple electrons, they're also going to be repelling each other. Okay? So they're going to influence the amounts of energy of the other electrons at each of these energy levels. So it made it so this formula didn't work. He didn't take into account for that. And the reason it worked for a hydrogen atom is because it only has one electron, and there are no effects of other electrons to cause changes in energy that are not understandable. But it does work for any other atom that has a single electron. So, for example, if I ionized one of the electrons of the helium atom, remember helium has 2 protons and 2 electrons. If I ionized one of those electrons, now it only has 1 electron, but it still has 2 protons. And if I plug 2 protons into that Bohr formula, then the energy levels calculate to be correct. If I have a lithium atom, remember it has 3 electrons. If I get rid of 2 of those, I now have a 1 electron system, but I have 3 protons. And if I plug in 3 into the Bohr equation and try to find the energy levels for this other electron that's left over, it works. And the same thing if I eliminate 3 of the beryllium electrons. Okay. On the other hand, even though as a model of the atom, the Bohr atom is incorrect, we still use the term ground state and excited state and retain the central idea that the energy of an atom occurs in discrete levels, and it changes energy by absorbing or emitting a specific photon of energy. So the Bohr atom was a quantum model. It's not quantum mechanics, okay, but it is a quantum model of the atom because it relates energy levels to a number, right? Energy level 1, energy level 2, energy level 3. So we call it a quantum model of the atom because it uses a knowledge of energy levels. Okay? Okay, now, how do we take this a step further? What happened next? The quantum mechanical model of an atom. Hopefully this all gets us to the point of understanding that matter and energy are just 2 different aspects of the same entity. This duality between wave and particle nature of things is called the wave-particle duality. We've talked about that. And remember, in particular, we use the concept of momentum to bridge the gap between these 2 aspects. So we say that energy equals mc squared, and we also say that energy equals Planck's constant times the frequency, and that allows us to equate these 2 things, and that allows us to think of momentum, which is a particle feature. Momentum is a particle feature that allows us to eliminate mass from that equation and say that a wave also has momentum. Okay? And then we can say that the wavelength, we can switch this up. And this is what de Broglie did. He said a particle with a mass has a wavelength. If we take the wavelength and do the same kind of thing here, rearrange the equation, we say that the wavelength has Planck's constant divided by momentum, and then we substitute mass times velocity in there, and we find out that even when we travel, have a wavelength. What was the thing though about our wavelength of larger things that made it so that we don't see this wave motion? What was the change or the trade-off between whether we were going to see the wave nature of something or the particle nature of something? Okay, what was it about the electron that made it so that the wave feature dominated? Yeah.
Just the electron is like so small that its like particle nature isn't as powerful as the wave nature.
Okay, so if we compare the wavelength of the particle to the size of the particle, okay, that's going to be the distinguishing factor, right? The wavelength of the electron is about the same as the size of the electron. In fact, the electron's a lot smaller. It's about 1,000th of the size of the wavelength. The wavelength's about 10 to the negative 10th, and the size of the electron is about 10 to the negative 14th or 15th in diameter. So the wavelength is actually a little bit bigger than the particle itself. So the wave features are going to be the thing that the behavior is most going to model. On the other hand, our size is so much greater than our wavelength. If we travel, our wavelength is going to be in the range of 10 to the negative 30 something. Okay? So I don't even know what those numbers are, 10 to the negative 30 something. Sextillions, heptillions, octillions, nonillions. I don't know what we get into. So, but those parts of a meter, we're so much larger than that our particle nature dominates. And so if that kind of a question or concept comes up, the key thing that decides which nature something is going to exhibit the most of, it's going to be their size versus whatever the supposed wavelength would be. Okay? So, because particles have wave features and electrons are particles with prominent wave features, and waves under certain constraints can only be maintained at frequencies or wavelengths or energies that allow the continuance of a standing wave. Yeah.
I was just going to say, like, the basic idea that we're trying to get from that is just the smaller the thing you're looking at, the more wave.
Absolutely.
Like, the more you'll see that it has a wave behavior.
Absolutely, and that's exactly what we're trying to communicate here. Okay, that's your understanding. Our understanding of physics makes it so that we have to understand that the motion of an electron is a wave. Okay, is that of a wave. Okay, we're not going to try and understand what this wave looks like because it would destroy our minds. But and I have to be honest, I never took mathematics in college that was at a high enough level, or even since then, that allows me to understand the Schrodinger wave equation the way I would like to. But I understand enough of this to be able to hopefully kind of communicate the concepts here. So electrons are, let's see, we need to have only certain energies, right? Because only certain energies allow this wave to actually be maintained as a standing wave. Electron motions in the atom are restricted to those motions, and they can only absorb or emit amounts of energy that will keep them in these wave motions, energies associated with specific frequencies of waves. Now we have to add one other aspect into this. And let's see, we only have 5 minutes. Okay, so it's going to take us longer to dive into this topic than 5 minutes, so I'm going to suggest that we stop right now.